think B is true, click on it. If it's false, don't click on it, right? Quick revision. Have a go. Come on, you're late. Grab your phone, quick. Click on the ones that you think are true. 20. One minute, I can spend 1 minute. 49 seconds. Hey guys, grab a device and click on the ones you think are true. Two minutes, okay. All right, let's have a look. $15.4, $14.4. How you doing? Oh, you missed out on the fun. Now you get the answers. Jeez. Nice style. So A, both TCP socket that accepts connections and the new socket returned. Remember when you guys did your first prac, you had a server type socket, and when you accepted a connection, you created a new socket, right? Okay, so when your client was connected, your client, was it talking to the server socket or the new socket? Long time ago. First prac, right? Sorry? Yeah, it talks to the new socket, right? And why is that important? Because what does the server socket have to do? What's the server's job? Come on. What happens if the server socket is busy talking to your client? Can the server socket service other clients? No. Exactly. The server socket continues to listen to new connections from other clients, right? So both the TCP socket that accepts connections and the new socket returned when a connection is accepted will share the same local port number. So you know that there are two sockets, but what's the port number? Are they going to be the same or different? So most of you may have used 8080, right, for your server socket. You're listening on port 8080. You got a connection request. You create a new socket, give it to the client. The client deals with that socket. You have a server socket and a new socket created for your client. Do they use the same local port number, which is, if this is 8080, is the new socket going to be 8080? Yeah. Yes. Why? How does the client know the difference between whether to go here? Sorry, how does on the server side, the networking stack know when it gets packets to give it to the server socket or the client socket? Don't expect you to know the answer because, it does do demultiplexing. So TCP demultiplexing uses 4 fields, right? 2 IP addresses, source destination port numbers, right? But the way it tells the difference between the two is that if you're making a new connection, do you remember the 3-way handshake? What do you need to send? A SYN, right? So if I'm a client trying to make a new connection, I would send a TCP packet to port 8080, maybe in your case, but with the SYN flag set, right? So that means I'm trying to make a connection, and that would be sent to the which socket? The server socket, right? So that's how that works, okay? So both of those sockets have the same port number, But if you're trying to make a new connection, then you would send a packet with the SYN flag set. Do you remember the flags on the TCP header? Right? And that's how you tell which socket to hand that packet over to, right? So I think all of you said 23, so that's fantastic. They do have the same port number. B, the sequence space in an implementation of go back in must be at least twice the window size. So, 4 of you are still not convinced. So we discussed this a while ago. They could be, right? But not must be, right? Okay? How big do they need to be? And yeah, the window size of the sender plus a receiver. Receiver is 1, sender is n, so it should be n plus 1. It could be larger, but that's the must, right? Okay, and we went through an example in class. If you're not convinced, come and chat to me after lecture. See me in my office, right? And we can talk about that, right? If a TCP sender currently has a congestion window of 8,000 bytes, then it will be able to send this many bytes if it has the data ready to be sent. Is this true? So the congestion window says 8,000 bytes. Can the TCP just go, yep, sending 8,000 bytes? True or false? Most of you think it's true. So know the answer to the question. But go back to congestion discussion that we had. When TCP was trying to determine the window size, it was using 2 fields, right? Congestion was not the only thing it was dealing with. What was the other thing it was dealing with in terms of a link? What could happen if you try to send too much data? Yeah, flow control, right? What happens to your receiver? You overwhelm the receiver, right? Remember? So how does TCP deal with that? Think back, quick. What was it called? You already said it. One more person.
Receiver window size?
Yeah, that's right. Receiver window size. So it's to do with flow control, right? Okay. So the way it does flow control is by maintaining 2 different states. One for congestion, one for flow control. So it can't just look at the congestion window size and determine it can send this many bytes. It has to find the minimum of the congestion window or the flow control window, right? Because you don't know what the problem could be, right? Okay, maybe the sender can't accept that many bytes. That is determined by the receiver window size. Or maybe the network is congested. That's determined by the congestion window size, right? So it has to be the least of those. So that's false. So you guys need to fix that part, right? So most of you are wrong. Last one. The congestion window grows more slowly in slow start than in congestion avoidance. So that's really great to see. So slow start is kind of, it's not really slow, is it? Right? It's actually quite fast. It doubles every time, right? Okay. And in congestion avoidance mode, it increases linearly, but it doubles in slow start. The reason we call it slow start is because we start from 1, right? Okay, 1 segment size. So good job. But C, if you're not sure, come and talk to me, right? Hopefully it's clear why that's not the case. Have a go at this one. We did something similar last time. Maybe we did it all. I think we did this already, right? So if you did this already, you should all know the answer. So how many bits are allocated to the network in this address? Shout out. How many bits are allocated to the network in this address? Quick, shout. How many? How many bits? How many bits for the network part? Sorry? 22. Still don't know who said it, but thank you. 22. Oh, yeah, thank you. Thanks. 22 bits, right? So which part of the address should be set to 1 for broadcast? Which? Network part or the host part? Host part. Good. Okay. So how many bits are allocated to a host? 22 minus 10, 32. 10 bits, right? So what do you get when you set those 10 bits to ones? Quick. $19 submissions. Right, let's have a look. 20, we had 24 last time. 21, a few more people. 22. Okay. So the right answer is C. Why is that? So your address is 200.2316.0 and 22, right? So essentially, what you have is this part is going to be set to all ones, right? Okay. So the division is going to be somewhere in here, right? So we have 16, and then there's 8 bits here. There's 2 bits that belong to the host part, right? So this is the 10 bits for the host. So all this is going to be set to ones. 2 of these bits at the end are going to be set to 1, right? So if I set these to 1, so that's 2 to the power 0, that's 2 to the power 2, 2 plus 1 is 3, right? In decimal, that's a 3. So the value for this part is going to be 16 plus 3. So 19, right? And 255, 23, and 200, right? So you end up with C as the right answer. Yeah. Oh, you could, but when you use IPv6 you will, because the numbers are so large. Decimals not enough compression. Right. All right, cool. Don't know if you should do the next one. Let's have a look. Try the next one. Oh, well, you could see it on the device, but yeah. I have 37 minutes to do routing. I can do it. So we ended the, oh, sorry, hots bits. Sorry, it should be, it should be host. Sorry, it should be host bits. So if you enter the host bits dot subnets, then that would work. Sorry. Huh? I did that in 2 places. They're at hot bits. Twice, geez. Where is it? Where's the other one? Create subnets on. The subnets need to support 60. Oh, yeah, hot siege. Sorry. Clearly, I was thinking of other things. Just kidding. Oh, it's a spelling mistake. So think, how many bits do you need to support 60 hosts? How many bits do you need? Bit of binary, 2 to the powers. 6? Yeah? How many hosts do you get with 6 bits? 64? Yep, sounds good. Cool. And then remember, you got to reserve 2 addresses. The all 0 for the network, all 1s for broadcast. So 62. So 64 minus 2 is 62 hosts, which is less than 60. Well, cool, right? There are 2 reserve addresses, remember? All 0s, network, all 1s, broadcast. So, yep, 6 bits. So, if you take out 6 bits, how many networks can you create? So in this address, you have 22 bits already allocated to network part. So that means how many bits are remaining for hosts? 10, right? From those 10 bits, how many do you need to allocate for the supporting 60 hosts? You already said that? 6. So how many bits are remaining to create networks? 4. Okay, so almost know the answer. Let's type something in. So number of subnets are come on, be brave. You almost have the answer now. Just have to type it in. "33 minutes. Mm-hmm. You're welcome to have a chat. 15, 16, I'll wait to 20. 3 more people. Whoa. A lot of answers. So we have a 616, 616. Why do you need to amalgamate? Oh, that's weird. Okay, I thought it would sort or accumulate the answers. But looks like a 616, right? 64, 16, 10, 16. Okay, so let's have a look. So essentially, you have from this network, you have 32 minus 22 bits, right? So which is you have 10 bits that you can play with, right? You've been given a network address. You have 10 bits that you can play with. From the 10 bits, you know you need to allocate at least 6 bits because each of these organizations or networks need to support 60 hosts. So 2 to the power 6, that's 64 is obviously less than 60 plus 2. Why 2? Because this is broadcast and network, right? So we need to separate 6 bits. That gives you 4 bits, right, left. So we can create networks or subnets with 4 bits. So that essentially becomes 2 to the power 4, which is what, 16? 4, 8, 16. Right? So we can create 16 different subnets. Okay? Now, no, I don't need that yet. My plan is to finish part of routing today. So getting on with the lecture and where we left off, right? Essentially, we talked about the network layer, we talked about addressing, and so IP protocol. And today I want to focus on routing, and I'm not going to talk about IPv6. I'll come back to that because just to set you up for your next prac, okay? So a quick example in terms of how data travels across the network. So here, let's assume that this host A has this kind of routing table, right, inside, okay? So it says that if the destination of an IP packet is 223.1.1, then this is in the same network as the host, right? So you can see the network here is 223.1.1, okay? So anything that's going to this network, it doesn't need to go anywhere. You can just send it directly to the machine, right? So give the packet to the link layer, and the link layer will send it to the host, right? Because they're on the same machine. But if anything is destined to 223.1.2, then your next hop or the next destination for that packet is going to be the router interface, right? Because this address is not in this network, right? So therefore, it needs to be sent to the router, and the router will know what to do, right? Okay, that's how routing works. You send it in the general direction of the destination, right? Anything in 223.1.3, which is this network, you send it to the router, right? So this is its next hop. Okay, that's what this routing table means. And this tells you number of hops to the destination. So that's 1 and 2, right? Okay. Is that clear? The general information in the routing table? Okay. So let's look at how a packet travels across this network, right? So let's assume that you want to send a packet from A to B. So that means when you get a packet, IP packet, IP datagram, packet, I guess you can use for datagrams. I might use them interchangeably. So if you look at this datagram, you can see that its source address is 223.1.1, destination, right? Destination address is 223.1.3. So when you look at this packet in the routing table, it tells you that actually this packet is going to a host on the same network. So all you have to do is give the packet to the link layer, which we haven't talked about yet, guys, which is just below the network layer. And the link layer will take care of sending that across this network to B, right? It'll put it into a different packet format called a link layer frame, and it'll send it to the same network, right? So there is no next hop for this, right? Okay, same network. Nothing needs to be done. Straightforward, right? So, slightly more complicated example. Let's say you want to send a packet, IP packet from A all the way across to E. So in this case, the routing table on host A will tell you that if the destination has this network address, so this, remember we're doing longest prefix matches here, right? So that's that one there. Then, so this is the network that it's going to. And this is not my network. So the next hop should be the router, right? And the router will know what to do. The router will have a routing table which tells it how to route it, right? So the first destination is to send that packet from A to the router interface, okay? And at the router, it'll have its own routing table, right? So this thing is in the data plane of the router. And so when it gets a packet, it'll see the source is 223.1.1, doesn't matter. It looks at the destination and it goes 223.1.2.2. So its routing table will tell you that if it's going to this network, it goes, oh, well, you know, I'm directly connected. My outgoing link should be 223.1.2 should be its interface here, right? So basically it forwards this packet from this interface to this interface, right? Based on this routing table. Okay? Yeah. Right. So the router does. And eventually, once it's here, this is on the same network, right? So the link layer takes care of delivering it from here to here. Okay? Right. So that's kind of what happens all the time that you don't get to see. So what I want to talk about next, or after this, talking a little bit about IP, is to talk about how we generate these routing tables, right? Which is critically important in terms of how we deliver packets across a network. Okay? Is that simple example clear to you guys? Yeah, cool. So what does an IP datagram look like? So it's a little bit more, well, not more complex than TCP, but looks a little complex. So you're used to seeing version numbers, future proofing in case there's a new version. Oh, there is a new version. It's called IPv6. Header length. Why do we need header length? Because it's got variable size headers. So when you're processing this packet, you need to be able to determine how big the header is, right? Type of service is typically used, unused, or little used, but is sometimes used now, is to determine what type of data is being carried. Most of that is to be able to treat different IP packets with different quality of service, right? Maybe voice versus file download, right? Maybe you want to prioritize, if I'm having loads of IP packets in my queue, maybe I want to prioritize the voice ones over file download type traffic, right? Because there are delay tolerances that I want to meet, right? So that's what that's there for, but it's little used at the moment. Length field. The length field tells you the total datagram length from here to the end, right? This one we're going to look at next, which is about fragmentation, right? So I'll delay that. Time to live is kind of misleading because it's not really a time field, but essentially what it tells you is, gives you is a hop count, right? So what that means is that if you look at this network, remember looking at number of hops. So what that means is that if I want to get to this machine, 1 hop, 2 hop, right? There's 2 hops to get to it. So the reason for the hop count is essentially it's a kind of a safety mechanism. So if you send packets out in the network, every time a packet gets forwarded from a router, it will reduce this hop count or time to leave value by 1. So let's say you send a packet with a TTL value of 10. When it goes to the first router, it gets reduced to 9. And when it gets to the second router, it gets reduced to 8, etc., right? But if a packet arrives at a router with a TTL counter of 0, that router will drop that packet, right? So this prevents, badly routed or, I don't know, packets just hanging around networks for ages and ages without reaching a destination, right? And just clogging up the network, right? So it's a way of kind of cleaning out the system, if you like, okay? So this is determined to just say, typically it shouldn't take more than 10 hops, but maybe you have a TTL counter of 20 just in case to make sure that it gets there. But if somehow that packet doesn't get routed or ends up in some kind of routing loop, which we'll look at next, then eventually this packet will get removed from the system, right? Okay, so it's important. This is really important, right? So upper layer. So when you get a packet and you're in the network layer, how do you determine? So network layer is a piece of software all on its own, has no idea about TCP or what's underneath, right? So it's a piece of code that's running. How does it determine what to do with the payload, right? Who do I give it to? So the upper layer essentially tells you who to give it to next, the layer above, right? So typically, this is determined by a number. The number will determine which, who to give this packet to. So you can think of it like a hook between the transport layer and the network layer, right? Okay. So for TCP, there's a particular number you would put in here. So when you get the packet, the network layer knows, right, now I need to hand over this payload to TCP, right? Okay. So that is the hook between the transport layer and the network layer. What is the hook between the transport layer and the application layer? How does the transport layer determine who to give packets to? Using what value in the header? Yeah, it's a port number. That's right. So the hook between the transport layer and the application layer is a port number, right? The port number determines the end system that's going to consume that packet. So the upper layer determines the hook between, if you like, the transport layer and the network layer. Okay. Header checksum. You guys are used to seeing that. You've implemented it. So noticeably, this is a header checksum, right? So it's not over the entire packet, but just over the header. Why is that a sensible decision? Well, do we need to go over this part? Typically, would you need to do that? Remember anything about TCP? Yeah, it has its own checksum, right? So we just calculate over the entire packet. So if you're typically carrying TCP, then that means, well, there's already a checksum for that payload, right, that you're carrying. So this is just limited to the header, right? There's no point trying to do it several times. Actually, as you look at layer, the other layers also have their own error corrections, right? So, so you'll find that in IPv6, actually, they've gotten rid of that as well, right? But yeah, so it's limited to the header. 2 IP addresses, source and destination, 32 bits each, right? Options, there's a whole bunch of options. You can look at the RFC, but it does allow you to do other things just in case in the future, right? So the important parts are probably focusing on that and maybe the fragmentation part, which we'll look at next. So essentially, what happens is that when you try to send stuff across a network, there are loads of links, right? All different links may have different capacities. So it's called, it's defined by, another acronym. Maximum transmission unit size. Maximum transmission unit size, right? MTU. So each of these links may have a different MTU, right? So let's say this is an Ethernet link, right, where its MTU is 1,500 bytes. Let's say this is a typical WAN link, and its MTU is 576 bytes. Okay, so these are real numbers. So Ethernet. Right. So what that means is that the maximum size of datagram or packet that you can send across this link has to be 1,500 bytes. What this means is that the maximum size of the packet that you can send across this link is 576 bytes. So if you originally sent a packet with 1,500 bytes, when this router has to forward that packet onto this link, it cannot carry this size datagram, right? So the way that IP deals with this problem is to fragment the original datagram. That is, take this one and split it up into smaller chunks, right? So in this example, it's been split into 3 fragments, okay? So in order to support fragmentation, what IP datagram has special support for supporting this, solving this problem, is to have these 3 particular fields, right? So essentially, you have a fragmentation identifier which identifies these 3 as being part of this original packet. So because eventually you got to put it together, I need to know whether these belong together, right? Okay, and has what's called a flag, which essentially the flag gets set to 1 for all the fragments except the last one, where it gets set to 0. Okay, so it tells you that there's more fragments, and 0 says, oh, it's the last one. All right. And then you have what's called a fragmentation offset counter. So the idea here is essentially when you do get these fragments back, you need to be able to reassemble them, right, together in the right order. So the offset tells you the offset from the beginning, right, so you know how to put them back together, right? So that's how fragmentation works in terms of the IP protocol. So this solves a problem that networks have a maximum transfer size, transmission unit size, and those units, the host that's sending the data may not be aware of, or even this router may not be aware of, right? So therefore, the way to solve it is if you find a link that's smaller, right, chop it up. It's entirely possible that when these packets come here, they might get split up again because this link is smaller, right? It's entirely possible. So there's, some good news and bad news. I guess the bad news is who's doing all the fragmenting work? It's their, stop falling asleep, it's their, who's doing the fragmenting in this example? Which device? The routers, right? Do we want routers to be doing fragmenting? Not really. It just makes the network slower, right? They should just be forwarding stuff, right? We don't want it to split stuff up. I haven't told you, but who do you think is putting the stuff back together from the diagram? Should it be the job of the router or the end destination system? End destination system. If it's a router, what can happen? Sorry? Yeah, it does slow down the network, but then you don't know if it's going to get split up again, right? It's because you might just go to the next hop, get split again. So essentially, this reassembly is the job of the end system, right? Splitting is the job of the router, okay? So when you get all the stuff back together, the network layer here would put everything back and hand it over to the upper layer, right? The other thing I wanted to talk to you about is, so essentially, when you're sending stuff, if you look at the IP datagram, this side note here essentially says that if you don't think of the options, if you discard the options, typically your IP header is going to be 20 bytes. Okay, you can calculate that. It's 32 times blah bits. Sorry, and then your TCP without options is going to be 20 bytes. So if you're using TCP/IP, right? Forget about the application layer. Just using TCP/IP to transport data. So you're paying your total header cost is 40 bytes, right? So if you think of if you go back to this example here, let's say my MTU is 1,500. So the price that I pay to send my overhead cost for this is going to be 40 bytes is the header divided by the amount of data I can transport is 1,460, right? So I don't know this number. But consider this example, right? So if I want to send, now it's the same data, but I've split into 3, right? The overhead I pay now is going to be 40 divided by 576 minus 40, 36, right? So you can see that small overhead here we have a larger overhead, right? Ideally, you'd want to be doing this, right? But if you were to send large, really, really huge jumbo packets, what would happen to the network? What would happen to other people that want to use the network? Will they get to use the network? No, right? Because you're constantly pouring packets. So there's going to be contentions, right? So there's a reason why you don't want to have this so large, because you do want to share the network. But if you make it too small, then you pay a price in terms of overhead, right? Okay. "12 minutes to do routing." So, any questions on fragmentation? We told you that, started talking about the data plane and the control plane, started talking about the data plane having a forwarding table, started talking about the control plane having a routing algorithm. So we said the routing algorithm is responsible for generating the forwarding table. So what we're going to look at is one of those routing algorithms, okay? So before we look at that, typically we can think of, we can model a network as a graph, right? Simple idea. So all of these are, you can think of our, nodes on the network, right? Routers. Any other kind of hosts on the network. And then these are your links. And those links have some kind of cost. Cost really depends, right? How do we determine cost? Good question. So cost could be based on the amount of traffic, right? Higher the traffic, higher the cost. Cost could be the amount of money you pay for that link. It's a fiber optic link. You pay $10,000, but it's a coaxial cable, so it costs you nothing, so it's cheaper to use that. Depends, right? So cost could be a variety of things. It depends. Or it could just be the distance, right, from A to B, right? Okay, it has to go far, so it takes longer to go, right? Could be delay. So it's up to you to determine what that cost factor is. It doesn't necessarily have to be the distance you traveled, right? So we can model a network as nodes and undirected graph, with each graph, each link having a weight, the weight representing some kind of cost metric, right, for traveling that link, okay? That really depends on the network or what you want to achieve from the network. So the first kind of routing algorithm is called link state routing algorithms, right? Link state routing algorithms. So OSPF is one of the ones you will come across, is a link state routing algorithm, right? And they all assume that you have complete visibility of the network, right? So what that means is it's a centralized routing algorithm, right? So it's like saying this node here has full visibility, right, of the network topology, right? And it sees all the link cost, okay? So these link state routing algorithms are centralized routing algorithms where you assume that each node has full visibility of the network. So how do they get full visibility of the network? Well, you got to start sharing data, right? There's no other way to do it. So that means you assume that each of these nodes on the network is broadcasting to other nodes its link cost, right? So A says my link cost to B is 2, my link cost to C is 5, my link cost to D is 1, and broadcast the link state, right, message. So these guys will go, oh, my link cost to C is 3, my link cost to A is 2, my link cost to D is 2, etc., right? So they all broadcast these link cost messages, and eventually each node can build up a full picture of the network topology and the cost, right? That's the assumption you start off with, okay? And that's how it works. So this type of routing algorithms are called, so they're centralized routing algorithms, right? So this is what we're looking at, okay? The next one we'll look at is a decentralized algorithm, which is distance vector, DV, which doesn't assume that you have full visibility of the network. So you can also think of routing algorithms as being static and dynamic. Static is very easy, which is you as a human being can configure the route and they stay the same, which is really not going to work for most of the networks that we deal with. Other one's dynamic, which means that if the status of a link changes, then you go and recompute that routing tables again, right? Okay. So for example, we could determine the route and then fix them, right? Static, bad idea. But most routing algorithms are dynamic. What that means is that if this link was to go down, then A would advertise saying that my link cost to C is now infinity, cannot get to it. And then that information will get propagated throughout the network, and all of these devices will recompute their routing table, right? So they can dynamically adjust and recompute new routes, okay? So let's look at how this works. So it's nice because you guys should have already learned this in data structures and algorithms. Heard of Dijkstra? Hands up. Okay, fantastic. So this is going to be easy. So it uses essentially Dijkstra's algorithm, right? Which is finding the shortest path from A to B. Okay, that's what it does. So just going over the notation part. This just means the cost of a link. So in our case, that just means could be a 5, right? A to B, CAB is 5. So DV is the current value of the cost of path from source to destination. So that is what you think is the cost of going to V from A. So that's what that is. PV is a predecessor node along the path from the source to V that is next to V. So if I'm going to C via B, then B is the predecessor node, right? The one before last, okay? And N is a set of nodes whose least cost path is definitely known. So N is a set we want to build, right? Okay, starting from yourself, right? So the simplest way to look at it is probably with an example. 6 minutes. So, so the way it starts off is by, so this is typical Dijkstra's algorithm, right? So you start off by saying, well, I am at A, so we assume that we're running this or starting this at node A, so you already know your own cost, so you add that to the list of nodes of which you know the cost. Then you compute all the cost for all the adjoining nodes, right? So that means you compute the cost of all your neighbors because you're directly connected and you know them already. If you're not directly connected, right? If you're not directly connected, that means you set the cost to infinity. It means I can't get to it. I don't know, right? Okay. So once you've done that, then what you do is you loop through all the nodes and find the minimum cost path to iterative to all the other destinations. First, you pick up the W, right? Which is not. First, you pick up a node for which you don't know the least cost path, right? And then you add that to A, okay? Such that, so you cause the least cost path that you think that you don't know about and add that to A. And then you try to find from W, right, try to find the cost of getting to all the other nodes that W knows about, okay? And then you compare to see, is my cost, so this is currently, if you like, known cost, which one is smaller, my current cost of getting to V or getting to V via W, right? So you compare my cost of getting to V versus the cost of getting to V via W, right? Can I find a new path through W, right? Or is what I know the best, right? And then you update the cost of getting to the destination, okay? So the new cost of V is either the old cost, which is what you know about, or to V known, or known shortest path cost to W plus the cost from W to V. So let's just look at an example of that, right? This is probably easier to do it this way, huh? So if I was to run through that algorithm, so it would look hopefully something like this. So essentially you start off by start at A, right? And so you add all the adjacent cost from A. So that means what am I connected to? So I'm connected to B, right? So the cost of going to B is, let's say, is 2. And my previous node is A. I can get to C. The cost of getting to C is 5. Previous node is A. I can get to D with a cost of 1. Previous node is still A. And anything else, I have no direct link. So I set the cost to infinity, right? Okay. So then I go into my loop. So the idea is that now I computed my cost to go into my neighbors. Now I'm going to check if I can get from my neighbor to other nodes, right? But I'm going to pick the neighbor with the least cost path to get to, right? Okay. I'm going to see if I can get to a neighbor with the lowest cost, and then from that neighbor, can I now find a path to all these other places that have a lower cost than what I think they have, what I think I have, right? So essentially, the next iteration is I can pick, for example, in this case, so it looks like I can add D to my N, right? Okay, because D is my next lowest cost path. So I just doing this stuff here. Find W not in N such that DW is a minimum, right? So this is the minimum. Okay, and add it to N, right? So if I add it to N, I end up with A and D, right? Now I'm going to check, now can I get to other places from D with a cost lower than what I know of? Okay, so can I get to B via D? So if I go to D, that's a cost of 1 plus 3, right? But I can get to B with a cost of 2. So what I know, 2, 1 plus 2, so this is still lower, right? Yeah, so this is still my best route. Okay, I'm still recording, good. So next one, can I get to C? So if I go via D, I have a 1 plus 3 is a 4, right? So clearly that's smaller than my 5, right? 1 plus 3 is a 4. So that means I can get to C via D with a cost of 4. So I update my knowledge of, right, how I can get to C. So I found a better path via D, right? Then check going to D. So D is already done. So going to E. So I have a new path that's better than infinity via D, which is a cost of 2. And predecessor node is D, right? So I can go 1, 2. It's smaller than my infinity, right? My previously known cost. Okay? Are you guys following me? Yeah, so 2. And then can I get to E via D? Well, no, because, F. F is not a direct link to D, so D's cost of going to F is still infinity, right? It's no better than my cost, right? I can get to D, and D says I can get to F with infinity. I can already get to F with infinity, so it's infinity, right? So my next job is to find, add the least cost path to my set N. So if I look at this table, I have 2 choices, right? E and B. Now you can pick one, right? You can pick whatever you like. It doesn't matter. You should arrive at the same answer. Okay, that's the good news. So just to go with the slide that you have in in your diagram on the slides, I can pick E. So I have added A, D, and E.